Hello everybody and welcome back. Today we're going to be talking about pendulums and how you can use algebra to solve problems with them. So first of all, what we're going to be looking at is the situation where you have a pendulum here and it has a mass. The mass that we're going to say it has is 1 gram. And then also we're going to say that it has this length L, and L we're going to say has a length of 2 meters. And so what we're going to try to look at is what is the period of this pendulum. So what is the time that it takes to go back and forth between its extreme points. So over here and over here, this pendulum will kind of follow this arc. And so what's the time? So there's a formula for that. We have T equals 2 pi square root of L over G, where G is the acceleration due to gravity. And so we can just plug in values. So we can say that that equals 2 pi times the square root of 2 meters divided by 9.8 meters per second squared. And so if we plug that into a calculator, we can say that 2 pi times the square root of 2 divided by 9.8, and we get a value that T equals 2.84, roughly, seconds. And so does this make sense? So we can also think about this to try to make sure the units make sense in terms of this formula. So we have the period equals 1 over the frequency. And if the frequency is in units of 1 over seconds, which equals 1 hertz, then what we can say is that the period equals 1 over seconds, which in reality just equals seconds. So yes, this unit does make sense. Now let's also look at an example of how does this affect the motion of this pendulum. So what we have here is a graph that shows, let's say that this is theta. So if you have the pendulum sort of swinging like this, its angle would be that. It's how far it kind of goes. And let's say that it oscillates between 1 and -1. It doesn't have to be that. It could honestly be any sort of value. And so what we're going to say is that we can look at a few things at the graph. So for example, the period of this pendulum is the distance between these two things that we call crests. And then we also have troughs, which are these kind of low points down here. And so those are sort of the maximum end points. And then we also have this amplitude A, which is how far it goes away from that equilibrium position. And then also what we have, just really quickly, is an example of dampening. So a dampening force is something that causes the pendulum or spring to lose energy over time. And so in this case, for example, the pendulum's swinging this way. It could be air resistance, it could be something, but the point is it's acting opposite to the motion of the pendulum. And so what ends up happening is it slows down the pendulum and it causes it to lose energy over time. So if a pendulum would typically sort of look like this, where it has, kind of constant motion, well, then a dampened one would start off similarly, but then lose energy over time and sort of come back to its equilibrium position. And so that is the effect of the dampening force.